Okay, so lesson 3.5, we're going back into chapter 3 because there were a couple of things we didn't get through before break. So we're going to go back into that. But lesson 3.5 talks about curve sketching, which is actually a college algebra lesson. So you have seen this before. The difference is we're going to do increasing and decreasing intervals and concavity. So we're going to add in that first derivative and second derivative test. But finding your intercepts and finding your asymptotes, that should be review. So I will go through it carefully though, because I'm sure you don't remember it. But that's not new concept. Neither is finding these increasing and decreasing intervals and concavity. It's just kind of bringing all of it together in order to sketch a graph. That's what we're going to do today. All right, so this first one, I'm going to find my intercepts. I may need an extra sheet of paper here, so I'll bring that in if I need it. So let's first find intercepts. Okay, so if you are finding your x and y intercepts, basically what's happening on the x-axis and the y-axis is that one of your variables is 0. Either x is 0 or y is 0, depending on what intercept you're finding. And you don't even have to think about which one you're finding. Really, you just need to think about one of them has to be 0. So first, let's say y is 0. So f of x right here, let's say this is 0. So that means 0 equals 3x plus 6 over x minus 1. The other scenario would be what if x equals 0? So f of x stays and x is 0. Like that. So these are my two intercepts. My first one, if I multiply both sides by x minus 1, this will cancel out, and this is 0. And then if I minus 6, I get negative 6. And then if I divide by 3, I get negative 2. So x equals negative 2 is my x intercept. So I'm going to go ahead on the graph and put it at x equals negative 2. All right, and then if I multiply by 0 here, this would be 0. So the top would be 6. This is 0, so the bottom is negative 1, which means I've got negative 6 here. So my y-intercept, or f of x, equals negative 6. So at negative 6, I have an intercept right there. Okay. This is not a linear situation. A lot of times people are like, oh, I'm just going to connect those dots. You can't do that. This is definitely, these problems are not going to be linear, okay? All right, asymptotes. So vertical asymptotes are, in my opinion, very simple. That's when you're checking to see when your denominator is going to be 0. So when is this undefined, right? So this is when x minus 1 equals 0. So in this case, that is when x equals 1. So at x equals 1, right here, x equals 1, I have a vertical asymptote. So that means I'm going to use a dashed line to represent it. I've got kind of this invisible wall that will affect my graph in some way. Horizontal asymptotes are probably something you do not remember, so we're going to talk about that. One situation is when the degree of your numerator and the degree of your denominator are the same. So in this case, my largest degree I have in here is just an x to the first, so the degree is 1. Same thing on the bottom. The largest exponent I have here is an x to the first, so that's a degree of 1. Since those are the same, what you do is find the ratio of your leading coefficients. So right here, so my function looked like this. I am looking for, since these are the same, I'm looking for this leading coefficient here. So in this case, the ratio of that leading coefficient is 3 to 1, 3 over 1. This one is technically a 1 right there. Okay, so that means y equals, that is my asymptote, which is y equals 3 is my horizontal asymptote. So at y equals 3, I have this horizontal asymptote like that. Again, that will affect my graph in some way. It may not affect all parts of my graph. So it is possible that I could have something happening over here that keeps away from both of those asymptotes, but then over here, maybe it crosses there. That could happen. It is possible. Typically, when that happens, you have 3 sections, and it's the middle section that is the weird one. That one crosses. Okay, so I've done my intercepts, I've done my asymptotes, so I'm going to go ahead and box those in as answers because they did ask me to find those things. Then I need to find my increasing and decreasing intervals and my concavity. So I'm going to use a separate sheet of paper for that. That's where my first and second derivative test come in. So my first derivative test on this one, my function was this, f of x equals 3x plus 6 over x minus 1. So my first derivative test, the first thing I have to do is the derivative. So in this case, I'm going to use quotient rule. So this would be low times the derivative of the high is 3 minus high times the derivative of the low is 1 all over low squared. So again, that's review from first semester. Make sure you remember how to do that. And then I'm going to simplify. So this, if I distribute, would be 3x minus 3. If I distribute this negative and the 1, this would be minus 3x minus 6. And then I can simplify that. 3x minus 3x is nothing. So really, this is negative 9 over x minus 1 squared. That's my first derivative. So now I need to think about when would that derivative be 0 and when would it be undefined, right? Well, in this case, this would never be 0 because no matter what the denominator is, this negative 9 on top would never cancel out to 0 at least. So this is not possible. Usually I say it's 0 when the numerator is 0. So I would set this equal to 0. Well, that can't equal 0. And then it's undefined when your denominator equals 0. So when x minus 1 squared equals 0. So really that's when x minus 1 equals 0. So that's when x equals 1. So it's undefined at x equals 1. So that is a critical point. So then when I set up my table, I'm going from negative infinity up to 1. And then from 1 up to infinity, because the only critical point I have is at 1. So then I'm going to check some test points here. My test point on this one I'm going to say is 0. This one I'm going to say is 2 because it's within those intervals. And then I'm going to plug that into my first derivative. So because this is the first derivative test, you're plugging those test points into the first derivative. So no matter what, my numerator is going to be negative in this case. And when I plug in 0 here, we're squaring this. So no matter what, this is going to be positive. So I'm going to have a negative over a positive, which is negative. So I have a decreasing interval. Same thing with this one. No matter what I do, I'm going to have a negative on top, and I'm going to have a positive on the bottom when I square it. So this is still going to be negative altogether. So I have 2 decreasing intervals. So far, that doesn't tell me a ton. So I'm going to do my concavity now. So my second derivative test. All right, so now I'm going to find my second derivative. So I'm going to go back to my first derivative right here. And I'm going to do the same. I'm going to use quotient rule again. You could bring this up and make it to the negative second and then do product rule instead. Really not even product rule. But I'm going to do my quotient rule like normal. So my low times the derivative of the high, the derivative of negative 9 is 0, minus high times the derivative of the low. Now be careful with ones like these. So the derivative of the low, bring down your exponent, so that'd be 2. Leave your inside exactly as is and minus 1 from the exponent, and then times the derivative of the inside, which in this case is just 1, because the derivative of x minus 1 is just 1. Okay, then my low would be low squared, which is x minus 1 squared, which means that makes it to the 4th now. All right, then I'm going to simplify. So all of this times 0 is just 0. so that's nothing. These two negative signs will cancel out and make a positive, so I'm going to cancel those. And then on the outsides here, I've got a 9 and a 2 and a 1. I can go ahead and multiply all of those. So that's 18. And then I had an x minus 1 still. And then in my denominator, I had an x minus 1 to the 4th. So if I simplify this, this is 18x minus 18 all over x minus 1 to the 4th. All right, so same thing I did on my other one. When is this going to be 0? That's going to happen when my numerator is 0. When is it going to be undefined? That's when my denominator is 0. All right, so when is my numerator 0? This is when 18x equals 18, which is when x equals 1. This one, if I fourth root both sides, x minus 1 equals 0, which means x equals 1. So really this is an indeterminate form at 1. But again, that just means my only critical point is 1. All right, so I'm only going to be concerned about when x equals 1. So again, from negative infinity up to 1 and from 1 up to infinity. So I'm going to use the same test points. I'm going to use 0 and 2 again. But this time I'm plugging it back into my second derivative, which is right there. All right, so if I plug 0 in here, this is going to give me a negative 18 on the top, and this will be positive no matter what, because when I take it to the 4th power, it's always going to be positive. So I have a negative over a positive, which is a negative. That tells me that this is concave down. Remember, second derivative tells you your concavity. If I plug a 2 in here, this is going to be positive up on the top. And again, this will always be positive. So this is positive, which is concave up. All right, so now let's see what that means as far as my graph goes. So I know from negative infinity up to 1, so in this section of my graph, from negative infinity up to 1, I had a decreasing interval and it was concave down. So from negative infinity up to 1 in both of those cases, I had decreasing and concave down. So in this section right here, I know that my function is going downward, it's decreasing, and it's cupped down because it's concave down. Well, with this asymptote right here and this asymptote and these intercepts, that tells me it looks like this. If I could draw correctly. There we go. So it looks to me like it's something along those lines where it's curving like this and then heading downward. So it's concave down, it's decreasing, and it hit both of those intercepts, and it didn't cross either of those asymptotes because it was concave down and decreasing. That means it went that direction. All right, the other section, so from here up, so from 1 up to infinity, 1 up to infinity, I still have a decreasing interval, so it's going downward, but this time it's concave up. Well, if it's going down, if it's decreasing, but it's concave up, that means it has to look like this. If it's decreasing and concave down, it has to look like this, right? So concave down, concave up. All right, so that means in this section, in order for this type of a graph to happen, I would say that has to happen up here. Because otherwise, if I drew it down here like this, it's going to cross this asymptote, which just seems a little weird, right? Now, you can always check those things. So I made a whole lot of assumptions here. If I'm not sure about something, why not take like x equals 5 and just plug it into my function and see what it is. See if it ends up like I'm saying, right? Okay. All right, so one more, I'll do that in another video.